Differential calculus tracks the exact continuous rate of change for any system at any given moment. But that generates a secondary, arguably harder problem. If you only have the microscopic rate of change, how do you run the math backward to reconstruct the original system? We solve this using integration. It acts as the exact inverse operation to differentiation, designed to take those isolated microscopic data points and scale them back up into a macroscopic whole. There is an immediate hurdle to this reverse process. The act of differentiation inherently destroys certain pieces of data from the original equation. Because of this data loss, integration is an investigative process. We have to reconstruct a missing system state using only its mathematical exhaust. This chart shows the curves for x squared plus 2, x squared plus 10, and x squared minus 5. When differentiated, they all collapse into a single line representing a shared derivative of 2x. The rate of change for any constant is 0, so it vanishes. Integrating that 2x rate of change recovers the x squared variable, but the original constant remains permanently unknowable. We represent this gap with a plus c. This constant of integration means we aren't solving for a single definitive answer. We are solving for an infinite family of parallel possible curves. To begin rebuilding these functions, we rely on the power rule as our bedrock algorithm, adjusting exponents to reverse standard polynomial derivatives. Standard trigonometric and exponential functions have direct known derivative pairs, serving as our base cases. Sine maps to cosine, and e to the x maps to itself. These base forms are easily reversed in isolation. However, real-world equations are rarely isolated. We have to aggressively manipulate their complex structures to break them down into smaller pieces we can actually process. Unlike differentiation, integration has no universal algorithm that solves every problem. To find a solution, we must intervene and actively change the equation's structure. We can map our options using this taxonomy tree. We branch out from our base rules into specific structural categories: composite functions, rational forms, and products. We start with the first branch, composite functions. To solve these, we use a method called substitution. Substitution requires strict pattern recognition. We must scan the equation to find a nested function sitting alongside its exact mathematical derivative. Look at this composite equation. We have an inner function, x squared plus 1, multiplied precisely by its rate of change, 2x. We strip away complexity by translating these variables into a dummy variable, t. The visual noise clears, leaving a basic sine function we can immediately integrate. Substitution functions as a deliberate re-indexing of the system. We map the variables into a secondary coordinate space, execute the operation, and then revert to the original parameters. Moving down the taxonomy, we reach rational forms, which are fractions built entirely from polynomials. A common structural obstacle occurs when a linear function in a numerator sits on top of a quadratic function in the denominator. To process this form, we apply a specific decomposition rule. We algebraically force the numerator to become a combination of the denominator's exact derivative plus a new arbitrary constant. By imposing this rule, we force the single intractable fraction to diverge into two separate independent terms, each with its own solvable path. The first piece now presents a specific ratio, a function in the denominator and its exact derivative in the numerator. Because the natural log function differentiates into 1 over x, reversing this ratio always yields a logarithmic form. The remaining portion aligns with standard quadratic rules. Rational integration requires us to artificially inject new constants to shatter rigid equations down into elemental, digestible parts. The final major branch addresses equations where two entirely distinct families of functions are multiplied together. To isolate them, we deploy integration by parts, which functions as the exact inverse of the product rule from differential calculus. We deliberately assign one function to be differentiated and the other to be integrated. This shifts the mathematical complexity from one side of the equation to the other. We determine these assignments using the I-late priority hierarchy. This visual list tells us exactly which function family to differentiate first to ensure the equation simplifies rather than expands uncontrollably. This hierarchy creates a highly specific cancellation case. It triggers when we multiply an exponential function by another function and its derivative. When you expand this particular arrangement, The resulting terms perfectly mirror one another. The positive and negative elements mutually destruct, leaving a clean, concise solution. Integration by parts relies on deliberate, targeted erosion. We selectively chip away at the complexity step by step until we reach our base forms. Until now, we have exclusively calculated indefinite integrals. When we shift to definite integrals, we stop searching for a generalized family of curves. Instead, we use the antiderivative to compute the exact numerical value of an accumulated area. This shift updates our mathematical notation. The integral sign acquires hard boundary limits, anchoring the bottom and the top of our target area. To evaluate it, we calculate the antiderivative at the upper limit, and then subtract the calculated value of the lower limit. Watch the constant of integration during this subtraction. Because the constant exists evenly at both boundaries, subtracting the lower limit from the upper limit zeroes the constant out entirely. It vanishes. Applying boundaries strips away the theoretical possibilities. We anchor the curve to physical reality, allowing the calculus to produce absolute, measurable answers. Definite integral properties operate as specialized algebraic tools designed to exploit the physical, geometric symmetry of a bounded space. Consider this complex trigonometric fraction, evaluated from 0 to pi over 2. Attempting to solve this through standard algebraic erosion is nearly impossible. We bypass the algebra using the boundary reflection property. This property proves that an integral evaluated from 0 to an upper limit holds the exact same mathematical value if we evaluate the upper limit minus x. When we swap x for our upper boundary minus x, the trigonometric terms invert, but the accumulated area remains identical. We take our original integral and add it directly to this reflected version. Due to geometric symmetry, the new numerator perfectly matches the denominator. The complex structure triggers a massive cancellation, reducing the equation to 1. Integration proficiency depends on identifying architectural taxonomy, finding the structural symmetries, chained patterns, and products necessary to reverse engineer calculus itself.